Welcome to the garden. We're going to have a quick look at how your heat pump water heater works, but on the heating side of it. So this isn't going to be the way that the actual physical side of your heat pump works, in the sense of how does it turn air into heat, if you will. What we're actually going to be discussing is sort of how this feeds into the whole system within your house. If you want to know more about the actual refrigerant side of it, there'll be another video on here somewhere about it, because we're fridge people. But for now, we're just going to look at the heating system, and I'm going to look at it on this because I happen to have this system here. I've tested it, all the rest of it, and I have this manual lying around, or this diagram of the circuit lying around. Now, first thing to note with this system is that you've got your house part here and your mains, domestic, coming in and all the rest of it. You've got the outdoor version here that lives in your garden and pisses off your neighbour, and then you've got this area here by the dark black line, which is the thermal store of it in this case. And all that really is a big cylinder where the hot water's stored, and then a couple of pumps and flow measurers and a heat exchanger and a booster heater, because quite obviously they don't quite trust that it's just going to work anyway, and why would they? But that's all this is. And if you don't have the thermal store part of it, you will have, in wherever it is that you've got this installed, like crammed into your airing cupboard or your basement or your garage, wherever you've got it installed, you've probably got the heat pump here that's outside still. You'll have the cylinder inside, which is the big insulated thing, and then you'll have an arrangement of pumps to circulate the water through the heat pump and then into your heating system. So what we're going to do is we're going to start here at this number 6. All these bow ties are just valves. There's nothing scary about them. And we'll start with 6, which is the heater pump. It's some sort of pump anyway. It does the heating circuit on this particular system. So initially we start the pump and we go over here on this pipe and we come, oh god, that's terrible, mate, up there, out, down here and into your heat pump, and that's an isolating valve that you're supposed to put on your local circuit. Now this, at the rating condition here, is 25 degrees C water going in, and the air outside going onto it is 7 degrees C at your rating condition. And then when we come out of here, which is the water return to the system, this is your 35 degrees C part. So that's your standard rating condition, and we go back into the heat pump itself, down here, through the flow meter, which is partially used to check that this pump's actually working, because if they don't detect flow there, they know there's a blockage somewhere. Either the pump has failed or these valves are closed because the bloke serviced it and not opened them again, or whatever, some reason, not flowing, error code comes up. We go through here, through this heating-y thing, and then at this point, some's going to go that way. Most of it is going to come through here, where it hits this 3-way valve, and water comes in, and it says in 100 millimeters turn right, and down we come, and we go through here, back up through this bit, and down there, down here, and that's into your radiator now. This is your local system, and we're putting this 35 degrees C water. You note that this has come not directly from the heat pump, but it's kind of directly out of the heat pump. So you're doing your work, your refrigeration side here, and rejecting the heat to the water. And it's that water that then gets circulated into your radiators or local system on this diagram. Now, that leads you to the first question. Why do you need bigger radiators? Allegedly, you're always told that you need bigger radiators. Well, what happens is you have the general heat flow equation of Q, which is your heat, and that is equal to H dot A dot delta T. And Q is your heat, which is your watts, if you will, power, energy per time coming out of the radiator. H is your overall heat transfer coefficient of the radiator in this case, or whatever the heat exchanger happens to be. Everything has an H value. So your radiator does the spiral cooler, presumably, that's in there, jam, everything has got an H value. If you work in building, you probably know what an R value is, which is a thermal resistance. H is just the opposite of that. It's literally 1 over R. You might also have heard it being called U, which is quite a common symbol for letter for it. A is the surface area, or the exchange area, again, if you will. It doesn't have to necessarily be the external surface. It could be an internal if it's a shell and tube heat exchanger. But it's surface area. And then delta T is your temperature difference. Now what happens is that we need this Q to be fixed, because that's... Jesus Christ, that's bad. Sorry, that... God. That's horrific. Okay. Fixed. H, well, that's kind of fixed for a radiator that's got water inside it. It's got some surface area which is going to be made out of the same material and approximate thickness. Well, this is also relatively fixed. Your delta T, if you had gas, for instance, would be in and around, maybe you'd have 70 degrees water circulation temperature. So that means that your delta T, when you want the room to be 20, is 50 K-ish. Or 50 degrees C, but we use K because we're doing it properly. But when you use your heat pump water heater, and we're coming out of here, well, we're at 35 K. Not 35 K. We're at 35 degrees C, coming out of your heat pump that's going straight to your radiators. So now we're at 10 K. So what that means is that this heat is fixed because that's just how much heat it takes to warm your house up, or to keep your house at the right temperature to compensate for the heat that leaks out. Your H is fixed because it's a metal radiator. Your delta T has reduced because we're now pumping water at 35 degrees versus... That's not 10, is it? I was thinking it's 10 degrees across there, but so it's actually 15. We are experts. But it's either way, it's a smaller number than the 50 that you have from your gas. So what that means is that the only way you can do this is to increase A. So the answer is yes, you probably will need a bigger heat exchanger for it, whether that be bigger radiators, underfloor heating, something else, but you need more, probably. So anyway, back to the diagram. Ugh. Okay, we'll leave you off, mate. You don't want to be on there anyway. And then we come back, and we go back into the heat pump, down here, and then bang, and we're back into our circulation pump. And then we go back through here. Now, quite interestingly, you look at this, and you say, okay, fine. Well, why don't we increase the delta T so that we don't need the radiator to be as big? Okay, let's try it. So we're going in here, and we need to raise this above 35 so that we have a bigger differential when we get over here. And remember, your test point where you're rating when you read whatever the COP of your heat pump is on the packaging when you buy it is rated here. And they're measuring it, saying we've got 25 water going in, 35 water coming out, and we've got this much mass flow, and therefore we know that's what the COP of the system is, based on how much heat we put into here. But this bit over here is the bit that depends on how good your install is. And if your install maybe isn't the best for whatever reason, because it's not quite as simple as just changing a boiler, this could be where you're actually losing all the COP, and it might be nothing to do with the heat pump part of it. It probably is working fine. It's just a fridge, and they all work, or it's a heat pump. But fridges are all heat pumps, vice versa. Heat pump is anything that moves heat. They all work the same for the same condition, so any difference between one and the other is always down to this install part, which unfortunately people don't want to hear, but it is. So, what happens if we need more delta T here? Well, if we look at this pH diagram, which, again, if you don't know, go and look at another video, I'll have it on there somewhere. We're using R32, which is quite a common heat pump thing in the UK, and it could well be the gas that you have. And if we say it's 0 degrees outside, we're sort of here. And all this has got is got pressure up here and enthalpy, which is a measure of internal energy, or specific internal energy across the bottom. And then you've got these temperature isotherms here, and the density is these dashed lines here. Well, temperature is also just a measure of internal energy. So as you increase the temperature from, say, here over to here, you're going through here and you're adding energy, which is what you expect. And when you add pressure over here in the liquid region, these lines are almost vertical. Because liquid, when you pressurize it, doesn't really compress. It just gets higher pressure. That's how hydraulics works. And over here with the dashed lines, you can see that the density just changed massively for a vapor, which is exactly what you expect, that you can compress gas easily and you can't compress liquid easily. But if we start here, for instance, and we draw a line on our evaporating temperature, which is going to be whatever the temperature is below 0, and we'll just say it's somewhere around -10 or something. We're going to go from this -10 line that I can't see, it's you because you're all together, and we're going to go from -10 and we're going to go straight through this is the evaporating part, and we're now evaporating moisture or liquid in the coil that's outside, and we're going to go to 0 because that's what your outside temperature is, and we're assuming there's nothing fancy like no heat exchangers, which there will be. And now what happens is that you have to compress it, which is where your energy comes from that you're putting in through your power measuring device, whatever it is in your house. And we're just going to now just draw a line, just made up line up here somewhere that we can now go to wherever. And then what happens is we'll have some temperature above, because we need 35 coming out, which is here. The refrigerant itself will be condensing higher than that because you need heat exchange. So we'll put it just arbitrarily around this 50 mark here. And 50 goes to... where's 50? 50 goes there. So we're condensing there, and we're over here on the line. So what we need to do then is reject this heat, and then now we go through the heat exchange in the heat exchanger, and we condense and lose all the energy that's now going into your water to heat your house. And then it drops down to like it's not going to get to 0, but we've got to go past it, and we end up with subcooling. I have to drag you back a bit further, mate, on to about -10. And then we have the isenthalpic expansion through your expansion valve, and you drop down to there, which is where we go back into cooling. And this bit is the energy you take out of the air, and this bit is the energy you put into your compressor to do the compression work and pump the refrigerant around the system. And then this bit is the bit that you get out as the heat, which is how you end up with... you get some small amount of energy in, and then you end up with this total heating thing, which is larger. So what you end up with is seemingly greater than 1, i.e. you're generating energy. You're not, you're just taking it from outside. But then what happens, as we come up on this line here, because they're not perfect and not ideal, this bit here is fixed because this is your outside temperature. And then we come up and up and up here to raise the water temperature that you have coming out of your heat pump and therefore around your system. Well, what happens then is that we have to put in more and more energy, and refrigeration systems and heat pumps don't like pressure ratio. And the higher we go up here, the higher pressure we're at over here. So now we're increasing the pressure ratio, but this bit is fixed. So we can't raise this pressure any higher to be able to compress the same amount and come up with a higher pressure. So as we do this, the system gets more and more inefficient, and it takes you more and more energy to compress it to the higher amount as you come over here further, which means that your COP actually drops. So there is some point when it becomes most efficient for your compressor to run, and that's the bit that makes you buy the system. So that's what the manufacturers aim for. So now we've got that out of the way as to why you can't just heat it up more. What you've then got is the heat exchange from the water side, and we can say that Q, the heat again, which is still fixed, is equal to the mass flow of the water times the specific heat of the water times the delta T of the water. Well, now the Q is fixed, the delta T is relatively fixed by the outside temperature and our efficiency. The specific heat is fixed, it's just 4.2 for liquid water, which is what it is going in and out. So now all you can do is vary the mass flow. So now you have to put the mass flow up. And the higher the mass flow you have, if you rearrange this equation, you find that the delta T becomes smaller and smaller. So what that means is that the way that you do it is that you use your smallish delta T here, which your heat pump is quite efficient at doing because it's a low pressure difference. And the lower your pressure ratio, i.e. the in and the out pressure of your compressor, the more efficient the system is. And all we do is we increase this pump speed here and flow more and more water. So you have more water flow, but less temperature difference, and it balances out, or it's the theory that it should balance out anyway. And had it ready over here, mate. And you say, well, what about the hot water? Well, the way the hot water works is that you've got your input somewhere, here it is, and your mains comes in. This is your mains water in. That's your mixer valve. Like if it's in your shower, that will be just a mixer valve, and it's got a certain amount of hot water going in one side and cold the other. And then what happens is that you come through here, and this is on its way to the hot tap, and it comes through here to this flow sensor, and it hits this heat exchanger here, which is the plate heat exchanger. And what happens with the heat exchanger is that this flow sensor triggers, and the system goes, oh, you want hot water, mate. And it turns this pump on, which then circulates hot water, and it draws the hot water out of the top of the cylinder, through here to check it's working, and then through the heat exchanger. And the idea is that this water, the hot water that comes out of the top of the cylinder, then comes up and then dribbles all over you in the shower, your nice hot water. And then when you come out of here, you've now got the cold water that returns back to the thermal store. But then what happens when you need heat? Or you need heat for the hot water? Well, we come this way again, we go through this pump that's now pumping the water around to get it into the heat pump. And it goes back out of the heat pump, and that's at your, I think that's, is that 7 outside temperature again, 15 in, which is about mains water in the UK, and I think it's 65 out, is it? Maybe, can't quite remember. 15 degrees C water in, 65 out, 50 degrees, or 50k lift, and, 7 degrees C air on. And then you come back down here, through the heater, through here, and it hits the three-way valve, and it goes, oh, turn left this time, mate. It comes up there, and then goes back into the top of your cylinder. And now you've got the hot water from your heat pump that then gets circulated back around through this heat exchanger, which then keeps the temperature up on the water that goes into your house, or into your shower and your hot water. And it does this at much higher temperature because you want this higher, because there's a limit to how much flow you're going to get coming out of your shower and your hot taps, which it turns out is less, and you want it a lot higher than you do for covering your body with. So that is very, I would say quickly, it's not quick, but that is quite simply how the heating and the hot water system work, just from the water flow side of the system, mostly ignoring how the actual physical heat pump system works. But we did explain, looking at the pH diagram, why you can't just very simply increase this temperature difference to end up with more heat to make up for the fact that you have a smaller temperature, or you have a smaller temperature difference, and you can't really increase it, so you do need either much more flow or bigger radiators or underfloor heating or some way to increase the surface area to accommodate for it. So it does, from a heating side, it does actually make sense, the fact that people will say, oh yeah, you need bigger radiators and stuff. and all the rest of the joy that comes with installing your heat pump. Anyway, that's all she wrote.